Hello everyone, thank you for that introduction. So as you said, I'm presenting on topology-optimization-based additive construction. So in this presentation, I'll be discussing four main topics. Obviously topology optimization, how that works with compression-only structures, the 3D printing of concrete, and then finally a wrap-up of the presentation, including some future work, which will obviously include more 3D printing. So let's dive deeper and ask the question, what is topology optimization? And I'm pretty sure most of you know this answer. It's very important in the additive manufacturing of metals, which we also do at Rowan University. And it is because printing bulky structures is unrealistic. And so when you have metals, especially steel, printing that in a large scale can be expensive. So you use topology optimization in order to decrease the cost. And you can see an example here from ANSYS showing how the use of topology optimization can get you a final product that performs at the same caliber or even better than the original design. So if you want to integrate topology optimization with additive manufacturing or additive construction, whichever word you prefer, you have the benefit of overcoming labor shortages because you can develop skilled labor in the area of the job site. There's also a reduction in construction time and cost savings because you are using less material. And obviously when you are using less material, there's also a decrease in the carbon emissions and there is less wastage. So the combination of topology optimization and additive construction allows us to think about pre-construction sustainability rather than just how the waste or end-of-life structural components can be reused. And so topology optimization and additive manufacturing allows for the freedom of design, and obviously, again, it results in lighter structures. However, there are barriers. It's often expensive in the computational sense when trying to achieve the base optimized model. And on the additive construction side, the equipment is expensive. Also, if you're not doing compression-only structures, which is what my presentation focuses on, the addition of reinforcement while the printing process is occurring is often difficult, and of course it does not comply with existing codes or standards. So is topology optimization actually suitable for concrete? As we know, concrete cracks in tension, cracks in tension, which the reinforcement carries. So if you can see here on the hand drawing on the right, we have our compression lines and our tension lines. So at Rowan, we're trying to envision a system where we print on the compression lines and we add the reinforcement on the tension lines, and we would have anchorages in between them. And you can see on the left a very well-known diagram how the reinforcement carries the stress until the concrete cracks. So we've done a lot of work with the printing path of a specimen where we printed longitudinally, which is the first image, in the transverse direction to the loading, and then a combination of those two in which the direction alternated between each layer. You can actually see here what it looks like from the inside, and if you were to just crop one of those beams, you can see that it looks like cast in place. And we did this test to get the modulus of rupture, and you could see each corresponding to each of the beams. And so we're trying to use that to study the effect of the printing path on 3D printed structures. So obviously, again, concrete is good in compression, so we created an arch. And this arch was basically just a slab and then the main arch. And so we thought, if it's an equivalent beam, just 2 layers printed, how would the strength change as opposed to printing with an arch? And so we found out that printing a circular path would make your structure 10 times stronger than if you were just to print a simple beam. So now let's dive deeper into the optimization of compression-only structures. I'm mostly using Abacus for my research. Unfortunately, I don't have fancy videos for you because it takes a while to run Abacus. But I start with the CAD model, and then I add our materials, define the loads and the boundary conditions. For this specific example, you can see that I added a uniform load in the middle third of the beam, and that's because I wanted to force the software to make a single arch structure, even though the members are straight, but that's because Abacus mostly deals with steel, so it's not used to simulating for concrete. And so to get the bridge shape, and in order to account for our nozzle size, I created a mesh size that was 0.5 inches, and that is because our nozzle size is 0.5 inches. So when designing for 3D printing in Abacus, you have to take that into account. Obviously, your mesh size can be smaller than that, but there is that added boundary condition. And so doing this whole process gives that result. As opposed to the first example, you can see how putting a uniform load across the entire slab and adding a middle support changes the design. And so you can see the CAD model that was used for the print. And you can see that some members were removed, and that is due to the limitations of the printer setup that were being used at the time, because those inner members could not be printed in a continuous path. And as we know, printing concrete, it just extrudes, and so it's hard to extrude and retract, extrude, retract at a fast rate. Again, I changed the boundary conditions in Abacus. While this model did not produce the full 3 arches that I was expecting, I still continued with the arches in the CAD design, and so it'll actually be interesting to see how this changes the load capacity once I test the actual printed structure. So now I would like to talk about 3D printing of concrete, and so we're going to start with our equipment. You can see here our Scara Elite Roadrunner, which was bought from 3D Potter. We have a tube system, and that's what I was talking about before, that restriction that we had. And we also have an auger system now where we can continuously feed the filament through and have a nice deposition of material, and that makes extruding and retracting at a faster rate a lot easier. So in starting the process, first we start with the CAD design, as I've shown you in the last couple slides. You can use Onshape or Fusion, and then you export the design into a slicing software. 3D Potter recommended to use Simplify 3D, and we found that to be extremely useful. And then it can be exported into a G code, which will show you all the printing parameters. And then finally, as you can see, you have your print. And this is the structure that I have shown in the previous slides that is being printed. And you can see that it is being printed face up, or front face up, I should say. As I talked about, I like to simplify 3D. So I figured I would show you a quick demonstration of the parameters we use. First, we import the CAD model and make sure a process is assigned to it. Next, in the extruder tab, we set the nozzle and the layer height. And so the nozzle diameter the layer height is dependent on the nozzle diameter. And so you can also see that in the additions tab, which is showing right now, that purple line, we can use a skirt in order to make sure that the material is extruding well. And in the layer tab, sometimes you only want to print the perimeter. You can see that in the CAD model, which was imported, it's completely solid. However, it's only printing the perimeter, and that's because we asked the software to do that. And again, in the Others tab, that's where we define the printing speed, and so it changes based on which type of system we're using. So here you can see the side-by-side abacus simulation versus the actual print, both in the front view. The isometric views from the simulation are not pictured, and that's due to the fact that there were cavities inside the members in the simulation. And so we couldn't do this, obviously, because we were printing face up, and right now you can't print in air. But so the next slide will give you a better understanding of how that worked, but we hope to change that with the new equipment that we just acquired. So as I said before, here is a better image of what I was explaining, but with the knowledge from each simulation and each boundary condition change, afforded me the opportunity to create a design of my own that not only had one main arch, but smaller internal arches. And so the smaller arches will carry the load until they fail, and then it will go to the main arch, increasing its capacity. Despite the successful prints that were shown throughout this presentation, there were challenges. One of the bridges, as you've seen throughout this presentation, had slender elements because of the optimization, because it is known that optimization will give you more slender elements. And so due to the small thickness of the element and the stiffening of the joints, we observed a crack at the location you can see here, but we added a shrinkage admixture to the mix, and so that has been helping with our prints. And so another challenge is the interlayer bonding. And so you can see here that, as I have talked about before, just having a top slab and a main arch, it's often difficult to have those come together. Either they can be over extruded or under extruded and not touch, but you can see here that we have successfully achieved fusion for both of those objectives. So what's next for myself, but also Rowan University? I hope to test all the arches numerically in Athena and experimentally using our actuator, which you can see a 3D model of, courtesy of one of the members of our team who did a lot of work on that. And I plan to use hydrostone in order to level out the layers, because obviously you have multiple beads going across. And I put support blocks at the bottom in order to ensure that the legs don't slip out from under themselves. And you can see I've already tested the simple arch in Atina and have found that I have a very high compressive strength as opposed to the displacement. So we hope to scale all of the bridges to a larger size. This is a different color because this was used with commercial material for the sole purpose of trying to figure out the entire capacity in which we can use our printer. But I hope to do this with our material and in Atina and Abacus as well. Those simulations will obviously take a long time. So in conclusion, topology optimization works within a user-defined space to create a design. And so software such as Atina Abacus, they both start with A, allows the user to define the space, and slight variations in the printing path, whether it be straight or circular, can lead to a larger capacity by using the former, and continued analysis through Atina provides an idea as to the results from testing in order to validate the experimental values. And topology optimization can be used in different ways, not just for arch-like structures, but for other types of structures as well. Thank you so much for your time, and if you have any questions outside of, I hope we have time for questions, feel free to email me.
Thank you.